Hey folks, welcome to this episode on acid-base theory. So we've seen these differences between acids and bases before when we were studying them initially. We had acids that taste sour and bases that taste bitter. Now hopefully we never tasted them before and we just kind of took the word. But if you think about even kind of sour candy, they taste very sour and they're acidic. If we think about a lemon, if we squeeze that into our mouth, then we get that very, very sour taste. Our face puckers up and not a pleasant experience for some people. I love them actually. If you ever tasted soap, if you ever got in trouble, you would see that it tastes bitter. Not only that, but it's also slippery to the touch. So these are some very basic differences between acids and bases. In this unit, we're going to be exploring more about the characteristics and behaviors of acids and bases. Now, some of the similarities is that they both ionize or dissociate into ions. Now, those two definitions, dissociate and ions, are a little bit different. We'll talk about that in a second. But regardless of what they do, they form electrolytes. And electrolytes is a substance that conducts electrical current when it's in its ion form. So as you can see in this graphic here we have an acid that breaks up into an H plus and an anion, and a base that splits up into OH and a cation. Now, not all bases split up into OH, and that's why we have different definitions. In this case, these substances are acting like Arrhenius acids and bases. But as we learn more and more about acids and bases, we started to evolve our definitions to not only include these ones, but branch out a little bit more. These talk about hydrogen, proton donors and acceptors. This is all about H plus and OH minus, and here we're going to be talking about electrons. The Lewis definition doesn't trump all of these, it includes these, but evolves it a little bit more. So not only acids and bases do they form electrolytes, they are also corrosive and reactive as we've seen before. So what is the difference between dissociation and ionization? Dissociation is when you have an ionic compound and that breaks up into its ions. So in an ionic compound, we already have ions existing. For example, in NaCl, we have Na plus and Cl minus already existing. And between these two ions, there's an ionic bond between their electrostatic attraction. Now, when something dissociates, these ions split up into Na plus and Cl minus by themselves. But the key thing here is that these ions already existed as ions. Okay? So all we did is break that bond. When we talk about ionization, we talk about creating ions that did not previously exist. For example, when we look at this acid over here, and this is sulfuric acid, we have a hydrogen bonded to an oxygen, to a sulfur, doubly bonded. All of these bonds are covalent bonds, which means that they're sharing electrons evenly in these bonds here. So 2 electrons here, 2, 2, 2, 4, and 4. When something ionizes, it means that the electrons are split up and you create ions that did not previously exist. That means breaking these covalent bonds. Now, not all molecular compounds ionize because if they were sharing, there's a reason why they're sharing. But strong acids, for example, or acids in general, they typically ionize and they break off to form this H plus ion, and in this case, we create our sulfate ion as well. So a little bit different. We in both cases, our end product will be ions. However, it's how those ions are formed. If the ions already existed, then it's dissociation. If the ions did not exist and they were as a result of breaking covalent bonds, then that is called ionization. So when we look at acids, for example, one of the acids that we probably know about is hydrochloric acid, HCl, and that's created by bubbling hydrogen chloride gas into water. When that actually happens, the HCl will ionize. Again, this is a molecular compound. This is a covalently bonded compound. It will ionize into H plus and Cl minus. And the way that it does this, in this kind of equation here, this is called your dissociation equation. Now, even though it's ionizing, we still call it the ionization equation or dissociation equation. That term is a little bit more loosely used. But in any case, we have this HCl that breaks up into its ions H plus and Cl minus. Now, this is how a lot of textbooks and things you'll find online show this dissociation. But what actually happens is that HCl, again, reacts with the water. This H plus, as we call it a proton, the reason it's a proton, if you look at just a hydrogen atom has 1 proton in its nucleus and 1 electron. Now, if we strip that electron away, all we're left with is basically a proton. And so we show that as H plus. Now, in this case, this proton can't exist by itself. It actually bonds to some of the water that the HCl is existing in. and we produce an ion called hydronium. So if you can see here we have our proton, here we have our existing water, and what we see is we have an interaction between that proton and the water, and we create this thing called hydronium, H3O+. Now, simple covalent bonds is when each atom that's involving itself in that bond provides an electron and it shares the electrons. In this case, what we have is this water molecule where we have a lone pair of electrons here and a lone pair of electrons here. This hydrogen proton, which is positive, is attracted to this lone pair of electrons. And this type of covalent bond is called a coordinate bond or a dative bond. And it's when both electrons come from the same atom. So hydrogen doesn't have any electrons to share, this hydrogen proton, because it's devoid of it. So it's bonding onto either this one or this lone pair of electrons, and it's creating a dative bond or a coordinate bond. So this, let's say, for example, we had over here, this one over here, and it formed this one over here. So that bond is a covalent bond, but it's specifically known as a dative or coordinate bond. Now, in some textbooks, again, like I said, this H3O+ is how it exists, but often it's indicated using this shorter H+. We're going to try to use this one as much as possible. Sometimes it might just be easier to use that in some cases. So here's Arrhenius' theory. This is something that you should be familiar with. When Arrhenius proposed the theory here, it said that acids are things that form hydrogen protons and bases form hydroxide ions. So in simplified version, this is an H plus producer and an OH producer, or a donor and donor. And you can see some of the examples here. You can see that most of these Arrhenius acids are very strong acids. For example, HCl, we have sulfuric acid, we have nitric acid, and the bases all contain OH. Now, that's a limitation because we actually know that there are some bases that don't involve OH. So that's the reason why we had to evolve our definition. So the main one that we look at here is ammonia. Ammonia is found in a lot of products, in fertilizers, in explosives, in cleaning products, industrial and household, but it doesn't have any hydroxide ions. So if it dissociates, as in what we saw before, it can't produce any OH. That's the basis of the Arrhenius theory, that bases produce OH. Well, we know that ammonia is a base, and it doesn't have OH. So how can we explain this? Well, we have to evolve our definition. The definition that was evolved is the Bronsted Lowry theory, where acids still produce these hydrogen protons as an H plus donor or producer, but bases accept hydrogen protons. So in the case of ammonia, when ammonia is NH3, it can accept a proton to form ammonium, NH4+. Again, another dative bond. Ammonia would have the two lone pairs there. This hydrogen would be attracted to those lone pairs, and you'd create a dative or coordinate bond with that and create ammonium. So this is how it's acting as a base. This ammonia is accepting a proton, and that's how it's creating a base. Now, if we kind of put this together in terms of water, what we're going to see is that we also produce OH. So in this case, we've seen this before. This is a Bronsted Lowry illustration, which means that their definition is the same as the Arrhenius definition. An acid will have a hydrogen that it will donate or produce and donate to whatever there is. Now, for an acid to be an acid, it has to have a base. So it has to donate this to something. If there's no base, this can't be an acid. If there's no acid, this can't be a base. They have to have one and the other for that interaction to happen. So this HCl, this hydrogen, is being given to the water, which is acting as a base because it's accepting the proton. And what you can see, we form something called a conjugate acid and conjugate base. We'll talk more about this a little bit later. When we talk about bases, in this case ammonia we know is a base, but it doesn't have that OH. How does it act as a base? Well, once again, in this case, water is now acting as an acid. It's donating its hydrogen, and it's donating it to the base here to create ammonium. Now, notice, what else is created with this ammonium? OH. OH is a very, very strong base. So it doesn't directly dissociate into OH, but it does create it as a byproduct, which is a very, very, very strong base. Now, notice one thing, and we'll talk about this more in a second, and we have these things called conjugate acids and conjugate bases. Now, an acid is something that gives away a proton to something else. In this case, water is a base because it's accepting that proton. And it creates these conjugate acids and conjugate bases. So this acid created a conjugate base. The base created a conjugate acid. Now, this is a little bit more evident when we have a two-way reaction like this, and this is a weaker acid and a weaker base, that it can go both ways. When we see ammonia picks up the hydrogen proton from water, it forms ammonium. But if we went in the opposite direction, what would happen? Ammonium would donate the proton to the OH and therefore form NH3 and H2O. Now, for ammonium to donate a proton and for OH to pick up a proton, anything that donates a proton is an acid. Anything that picks up a proton is a base. And that's why something that is a base forms a conjugate acid, and an acid forms a conjugate base, because in this direction, that acts as an acid, it gives away the proton, but in this direction, its kind of pair here acts as a base because it would pick up a proton to reform H2O. So one kind of expansion to this definition was Lewis theory. And Lewis said, well, some of these things don't work with the protons, they don't work with the OHs, but still some things act as acids and bases. Now, if we look at this example here, methylamine reacts with water to produce a methylammonium ion and OH. So in this case, methylamine, in this case, what we're seeing is acting as a base. How is it acting as a base? It's not accepting any protons. It's not accepting anything else. In this case, well, it actually is in this case, but the key part here is all about these electrons. Acids, in case of Lewis theory, is anything that accepts a non-bonding electron pair. Bases are the opposite. It donates a non-bonding electron pair. So by expanding this definition, we have included a lot of different things, such as certain oxides and benzene, some aprotic things that don't deal with the exchange of protons. So as we were mentioning, these pairs that have an acid and base are known as conjugate base pairs or conjugate pairs. And the key thing is how they differ. They differ from one another through the presence or absence of a transferable hydrogen ion. So when it comes to this equation, we can identify the base pairs because ammonia has NH3, ammonium has NH4+. There's a difference of one proton here. Same with the water and the hydroxide ion. It's a difference of one H+. So when we do this, we usually use square brackets to identify how they're linked. There's that. And we also have this over here. So once again, in this case, if we wanted to figure out which one was the acids and the bases and their conjugates, we just look at the transferable hydrogen ion. These are all the same. So in this case, we have acetic acid reacting with water to produce hydronium ion and an acetate ion. And you can see that here are your Lewis dot structures on top here. So this hydrogen from the acetic acid, the CH3COOH, this is being donated, and because it's being donated, it is acting as an acid in the Bronsted Lowry and Arrhenius definitions. Now, this water is acting as a base according to the Bronsted Lowry definitions because it's picking up that proton that's going to be lost and creating a coordinate or dative bond to form hydronium. So that hydronium went from creating water where it had two hydrogens to oxygen now having three hydrogens. It picked something up, and because of that, this was acting as a base, and this created a conjugate acid. Because, think about it, if we went the opposite direction, how could hydronium become water? It would have to donate a hydrogen. Something that donates a hydrogen is considered an acid, and we call it a conjugate acid. So there's a relationship between these two. Okay, so this acetic acid donates, becomes acetate. If we went in the reverse direction, the acetate would pick up a hydrogen here and form our acetic acid, and as such, it's acting as a base, and we call it a conjugate base. So take a moment here and try to determine the conjugate base pairs. So do some square brackets and see if you can figure out how they linked, and also label the acid base, conjugate acid, and conjugate base below. So pause the video, and when you're ready to return, we'll give you the answers. Okay, so welcome back. Here are the answers here. You can see that acetic acid and water, we see that this is the acid and that's the base because the water compared to the hydronium here has picked up a proton, and so something that picks up a proton to become hydronium is acting as a base. Now again, if we want to go the opposite way, this hydronium would have to donate a proton, and so therefore it would be acting as a conjugate acid. We have HCN and OH. So in this case, when we compare HCN on this side and this side, this one is devoid of a proton, so it had to have lost it here to this. Something that loses is an acid, and something that gains is a base. Now, if we look at it in the opposite direction, this H2O to become an OH would have to lose a proton, and because it would have to lose a proton to CN, it is then considered a conjugate acid. And the same goes for the last one over here. Here we have ammonium and we have water. To compare ammonium and ammonia, this species over here has had to lose a proton to the water. Something that loses is an acid, something that gains is a base, and then we have our conjugate acids and our bases on this side. Now, something that's called amphoteric is a substance that can act as either an acid and a base. As we've seen in the previous examples, water is one of those substances. If it's interacting with a base, for example, in this case, it's going to act as an acid. You can see that the relationship between here and here, it's gone from having 2 hydrogens to only having 1. So therefore, it had to donate one of these hydrogens to this ammonia, and there's those lone pairs of electrons. It creates a coordinate dative bond and creates ammonia. Or it can act as a base, where it means it picks up a proton. So in this case, here we have a substance that has an OH over here. This substance would lose its hydrogen proton over here to create hydronium and create an ion form of that. Now, again, it all depends on what water is reacting with. If it's reacting with something that prefers to be a base, it's going to act as an acid. If water is reacting with something that prefers to be an acid, it's going to act as a base. So again, substances that can do both are called amphoteric. Now, just a word here. You might also see a word called amphiprotic or amphiprotic. Now, amphiprotic refers to any substance, it could be ionic or covalent, that can both accept or donate at least 1 proton. When we talk about protic, we're basically talking about the H plus proton. So amphiprotic refers to any substance that can accept or donate a proton. Now, all amphiprotics are also amphoteric. What that means is that they can act as acids and bases, which is what amphoteric is, by donating or accepting protons, which is what amphiprotic is. But the reverse is not always true, especially when it comes to Lewis acids and bases. So some species, they can act as acids and bases, but by accepting and donating electrons, they don't actually exchange any protons. And therefore, they are amphoteric, they act as Lewis acids and bases, but they are not amphiprotic because they don't accept or donate protons. So the more correct term is amphoteric, and that's what we're going to use in our course, is because it's all-encompassing. It doesn't matter if you exchange electrons or if you exchange protons. Amphoteric just means you're acting as an acid and a base. Amphiprotic is more specific. It only refers to those things that are exchanging protons, either accepting or donating. Now, something that's interesting about water is that water in its natural state actually contains both hydronium and hydroxide, and that's how we can get a pH from water. And when we look at this, it is a very, 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 very weak electrolyte, but it's electrolyte nonetheless. And the reason that it happens, electrolyte, remember, means that it forms water ions. So water actually breaks down into H plus and OH minus. Now we know that H plus can't exist by itself, so there has to be a different way. Well, it's when we have 2 water molecules reacting with one another. One of them will act as an acid, one of them will act as a base. In this case, if we look at our conjugates, we can see that there's a relationship here and here as well. So in this case, this water molecule has acted as the acid. It's donated its H plus to this, and this created the OH minus, and because this picked it up, this created the hydronium. And you can see that this is a reversible reaction. The reversible reaction is not equal. The reverse rate is larger, so more water exists in the form that we expect it to, but we still have this hydronium and hydroxide ions at the same time. So again, one of them is acting as a Bronsted Lowry acid, one of them is acting as a Bronsted Lowry base, and because of that, we will have at any given time hydronium and OH. Now that begs the question, if we have hydronium and OH, how come we're not acidic and how come we're not basic? Well, if you look at the stoichiometry, this is 1 to 1, so they cancel each other out and we don't get any overarching acidity or basicity. So thanks very much for watching. We'll see you next time.